of numbers. Let's start with the easiest numbers to deal with, the set of natural numbers. Set of natural numbers are the numbers that we use to count. 1, 2, 3, 4, 5, 6, and so on. Next, we have the set of whole numbers. The set of whole numbers is the set of natural numbers together with the number 0. So 0, 1, 2, 3, 4, 5, 6, and so on. Next, mathematicians constructed the set of integers, or also known as signed numbers, from whole numbers the following way. They place 0 at the center, positive numbers on the right of 0, negative numbers on the left of 0. This continues in both directions, to the right, to the left. Turns out these numbers are very useful. For instance, if you talk about bank accounts, it's not the same to have positive $100 in your account as a balance compared to negative $100, right? Okay, next, mathematicians constructed a set of rational numbers by taking ratios between signed numbers. By ratios, we mean fractions. Mathematically speaking, the set of rational numbers is defined as the set of all numbers p divided by q, such that p and q are integers, signed numbers, and q is not 0. Q is not 0, because remember, if q is 0, the division is undefined. So q never 0. Now, for you to visualize these are rational numbers. Examples of rational numbers are 1 over 10, minus 3 over 2, 1/3, 5 over 9. 1 over 10 expressed as a decimal is the same as 0.1. 3 over 2 expressed as a decimal is the same as 1.5. 1/3 expressed as a decimal is the same as 0.333 ... which is the same as 0.3 with a bar on top of the 3 to indicate that 3 repeats itself forever. Similar result is found by when you divide the number 5 by the number 9. You get 0.555, where the number 5 repeats itself forever, so this should be the same as 0.5 bar. Now, you can see here that the decimal representation ends. This is called a terminating decimal, whereas here the decimal representation does not end but repeats itself. This is called non-terminating repeating. Turns out fractions, when expressed as decimals, are either terminating decimals or non-terminating repeating decimals. So these rational numbers, in order for you to identify them in an easy way, they come in 3 forms. They are either fractions, as following the definition, right? Or terminating decimals, which is what you see here. Decimal terminates, or they are non-terminating repeating decimals. Okay, so if a given number either looks like a fraction or a terminating decimal or a non-terminating repeating decimal, then it is a rational number. Okay, now let's talk about the next set of numbers, which is called the set of irrational numbers. For that, let me go to the next page. The set of irrational numbers. These are numbers that cannot be represented as fractions. That's why they are called irrational numbers. Examples of irrational numbers are special numbers, pi for instance, which when computed gives us the following decimal: 3.14159 dot dot dot. It continues, non-terminating, non-repeating. This is the number pi. Then we have E, Euler number, which is approximately equal to 2.71828. Euler number. Again, you can see that it's non-terminating, non-repeating. Next, we can see that square root of 2 when computed is equal to 1.41421 dot dot dot. Again, non-terminating, non-repeating. Square root of 3 approximately equal to 1.73205 dot dot dot, non-terminating, non-repeating. So this is a irrational number. Then we can see this number 5.7272227 and so on. This number is non-terminating, non-repeating, even though it exhibits or it shows a pattern, right? So this should be considered also to be an irrational number. So irrational number can be easily identified by looking at the following form: non-terminating, non-repeating decimals. Okay, now let's try to wrap this up, put everything together. For that, let's go to their page. Real numbers. What are the real numbers? The real numbers are the rational numbers together with the irrational numbers. To put it simple, real numbers are all numbers that we have presented before. Natural numbers, integers, whole numbers, rational, irrational, all together. They form the system of real numbers, and that's the system we will work with. Now, for you to see examples of how you should identify given numbers, let me give you some here. Number one, suppose they say, given the number 4, classify the number 4. The number 4 is a natural number. It is also an integer. Remember, there is an agreement that says that if you don't see the positive sign, it's understood that there is a positive sign in front of 4, so it should be considered to be an integer. It is also a rational number, because notice this number 4, the same as the number 4 divided by 1, so it can be expressed as a fraction, so rational number. It's not an irrational number, because once it's rational, it cannot be an irrational number. Number 2, let's take a look at this number, -7. The number -7 is not a natural number. Natural numbers do not have signs. It is an integer. It is a rational number. The number -7 can be expressed as -7 divided by 1. So it's a rational number. And it cannot be an irrational number, right? Irrational numbers cannot be rational numbers. Number 3, let's take a look at this, -5.8 13. Minus 5.13, it is not a natural number. It is not an integer. It is a rational number because notice that when expressed as a decimal, this number ends. It's a terminating decimal. So terminating decimals are rational numbers. Number 4, 6.4 bar on top of 4. 6.4 bar is not a natural number. It's not an integer. It is a rational number because it's non-terminating, repeating. The number 4 repeats itself, right? This is the same as 6.4, 4, 4, 4, dot, dot, dot. Okay, number 5, let's take a look at this number, 18.35, 335, 3335, 33335, and so on. This number is not a natural number, it's not an integer. It is not a rational number because it's non-terminating, non-repeating. Even though there is a pattern, it's non-terminating, non-repeating. There is no way to place the bar on top of any of these numbers on the decimal expansion. So this must be an irrational number. Number 6. What about the number pi? Number pi is not a natural number. It's not an integer. It's not a rational number. It's a special number. Remember, its expansion never ends. It's non-terminating, non-repeating. So therefore, it must be an irrational number. What about this number? Square root of number 6. The square root of number 6 is not exact, right? Remember we mentioned that square roots and in general radicals that are not exact, they are irrational numbers. Square root of 2, square root of 3, square root of 5, square root of 6 is not exact, so it must be an irrational number.